Huh? I don't know. We need to look at that. We need to. I think it's actually the week. It's the class before the final exam, so it'll be October to something. Okay, guys, can y'all see this? So I am sharing my screen, right? Okay. So what we're going to look at today is the transmission of mechanical power, which is a very important part in mechatronics to understand. In fact, this was originally the way the term came out on mechatronics. There was a Japanese company, and they dealt with both electronics and mechanics. And one of the engineers wanted to come up with a term that basically says what they did, and they come up with mechatronics. So originally, mechatronics was just a combination of mechanical and then electronic or electrical. But what over the years, mechatronics has basically become involved with everything that deals with manufacturing. So drafting, cab, welding, anything that deals with mechatronics, anything that deals with manufacturing is part of the mechatronics now. But of course, the name hadn't changed at all. So what we're looking at today is we're looking at the mechanical section of transferring power. And so we'll start off by looking at gears. We'll look at the type of gears, terminology and nomenclature, force transmitted, and the design of what we call a gearbox. So we'll start off with looking at some terminology. So a gear is a toothed wheel that engages with another toothed wheel in order to transmit motion and power. The drive gear, this is the gear in a set of gears which transfer motion and power to the other gears in the set. So it's usually the driver, it's usually the first gear. So your prime mover would connect to the driver gear. So like your motor, the first gear it comes in when it goes in your transmission, the first gear it sees would be the driver gear. The driven gear, this is the gear in a set of gears to which power and motion is transferred by other gears in the set. So you start off with the driver, and then every gear after that would be considered a driven. Then we have pinion. Pinion is just the smallest gear in a gear set. And then the gear, most people call it a pinion gear, but just pinion, and then the gear would be the largest gear in the gear set. Torque, a twisting force that causes or tends to cause something to rotate about an axis in a point. Sorry. And there's a glossary on the Blackboard site. There should be a mechanical section or this class section where you can go back and look up these terms. So basically, when we're looking at work, of course, this is speed versus torque. So if torque goes up, speed goes down. So you look, we come up here and we start off with, and y'all don't have to memorize this chart. This is just, y'all memorize this chart. We're not going to use this chart again, by the way. All we need to understand is the concept of work. So, of course, we rate torque. One way we rate torque is something called horsepower. And that's what was developed. Y'all know how that term came into play? Yeah, horsepower. Well, the problem is the steam engine was coming in, and people didn't understand the work that a steam engine did. So basically, they hooked up a steam engine to a weight, dropped it down in a well, and they wheeled it up and saw how fast it could come up. It could bring that weight up in a certain amount of time. Then they took the horses up, and they did exactly the same thing. And so they came up with so many horses would do the same work. So now, as a steam engine, so if they said it was four horsepower, they understood now because all they've been dealing with all their life is horses, right? You understand? So basically, it was a way of associating a steam engine with horses. And so it's an interesting story. But what happens if if we're doing a twisted motion, so if you notice here, torque, if speed goes up for the same horsepower engine, then the torque is going to go down. And you can actually see this in your car. So what we do is we start off with very low speed. It gives us very high what? Torque. And then as the car comes up to speed, we start shifting through that thing, and we're increasing the speed because we don't need that torque anymore. Okay. So horsepower is an interesting thing. Most of the rest of the world don't deal with horsepower. They deal with kilowatts. So it's about 746 watts per horsepower. So you won't find any engines. Well, I don't know about car engines. They probably, but if you deal with electrical devices, they're going to deal with kilowatts over there. But this is just a chart that shows you when speeds goes up for a certain, the torque would go down to deliver the same amount of horsepower, which is pretty interesting. We need to understand the different types of loads. I had a spinner that I used to show this on, but I have no idea where it is. But a load that is perpendicular to the axis, we call that a radial load. And then a load that is parallel or in line, we call that an axial load. Does that make sense? So usually when I spin it, I'd spin it this way, and I'd say, well, this is an axial load, and I'd turn it like that, it would be a radial load, but I don't know where it's at. So gears.
You find them in your engines, in your transmission,
which is pretty neat, right? But at the very end he says, not taking in consideration friction, right? You understand that? So it always takes a little more work on the driver than we get out of the driven. So if your gear reduces, so if the output gear is bigger than the input gear, then you reduce the speed but increase the torque. So basically work is equal to, or torque would equal to be the speed times distance. So if speed goes up and distance stays the same, then torque goes down, right? Or vice versa. So these are the type gears. We'll look at spur gears, helical gears, bevel gears, and also worm gears, which is the one that he just got through talking about. Now, unfortunately, we can't see the gears over there on our manufacturing line. All our motors, by the way, are little old tiny things, and I've got one around here somewhere. So, but what they do is, if you look at them, we got the motor, and then on the outside, it's got a block on it like this. And this right here is the actual gearbox. And every one that we have are torque multipliers. So you hear the motor running really, really fast, but the output is actually running a lot slower. And when we go over there and look at them, it's actually got the gear ratio, and it's not separable, but it's got the gear ratio on the front, like 13.5 to 1. Or something like that. So it actually tells you the gear ratio between the input and output. These are all the motors that we have on our manufacturing line. So every one of them are geared motors. Now, how the gears are set up, whether they're spur gears or helical gears or bevel gears or worm gears, we don't know because the actual unit is sealed. So these are spur gears. So this is probably the ones you see most often. These are the most widely used gears, and they're used to transmit torque between two parallel shafts. Are we okay? So spur gears. So you notice these are the easiest to make. They're very easy to make as far as gears goes. Okay. These are helical gears, and you can see these the actual teeth is cut in an angle. These guys can transfer more torque because they have more surface area when they're also quieter because the gears don't match, they don't clank together, they actually mash and slide into each other. The only problem we have with helical gears is they create a lot of they create a lot of actual load. With this thing, they're actually trying to push each other apart, right? You understand that? So these guys, they create a lot of actual load. They try to pull themselves apart from each other. So they came up with with a double, what they call a double helix, where you notice the slots in the gears are actually opposite of each other. And so you still get the surface area, you still get the torque, the nice transfer of torque, but these basically eliminates the actual load, the load that's trying, not axle, A-X-I-L, axle load. Biggest problem with these, of course, they're a lot harder to make because you have to bevel them in together. These are actually two just standard helical gears, and notice they're just mounted on the same shaft. So this one will be pulling it one way, this will be pulling it the other way, and so that keeps them from trying to, and they cancel out. These are actually machined this way. So these are actually machined, so this would be a lot more difficult to machine than this type of gear right here. So the advantage, helical gears, they run a lot smoother. And helical gears, they run a lot smoother and they can transfer more torque. The biggest problem we have with standard helical gears is they try to pull each other apart, right? Y'all understand that? Because one of them's angled this way, one of them's angled that way, and it's like two screws trying to. It's like basically you get the nut and the screw, and when you turn one, what happens? The nut moves, right? You understand? And that's the problem we have with the regular helical gears. So this would be like the threads in one of them would be like the threads inside the boat, and the other one would be like the boat. But they're mounted on shafts, and they can't move, but they're trying to pull each other apart all the time. So this will eliminate that, but this comes up, and this would be expensive. So these are really quiet. They basically don't have any actual load to them because they cancel each other out. These are bevel gears. So we use bevel gears for intersecting gears. And you can see we have both the ones that's geared like a spur gear, and we have the ones that's geared by like a bevel gear. So these are actually, like a helical gear. And so we do this to basically change the direction of the rotation. I mean, not the direction of the rotation, but the direction of the shafts. This is a worm gear. This is the last one he talked about. These are they give us really, really good torque characteristics. These transmit motion between two parallel shafts and non-transmitting shafts, depending on the number of teeth engaged, called single or double. The problem we have with this, though, is that we're only engaging a few little teeth. Can you see we got that gap there and your gap there? So to get higher torque, what they'll actually do, I don't know if they're going to come up here and show this, but I've actually seen them where they're actually basically slotted in the center like this. And these can transfer more torque because you have more teeth that's engaging at the same time. Are we okay on worm gears? Okay? Questions? Guys at home? The gear modulus. So what we got is we got different size gears, and when they mesh, of course, we got to have one gear tooth that engages and goes into the slot of the other. So, but the gears themselves can actually be different sizes. So what we have to do, if these gears are going to mesh correctly, then that means the size of the teeth has to be the same, right? You understand that? As far as the depth. Sometimes, by the way, they'll clip off this little end because it doesn't do any work, and it makes the tooth smoother as far as transitioning in. So what we have is what we call a gear modulus. So if two gears have the same modulus, it don't make any difference how big they are or how small they are. That means their teeth would mesh. That makes sense? Everybody okay? So smaller gear is what we call a pinion gear. Largest gear is called a gear. In most applications, the pinion gear is the driver, and not all applications. So it depends on whether you want to increase torque or increase speed. Does that make sense? So if our driver gear is smaller, if our pinion gear is smaller than our driven gear, then it will be a torque multiplier and be a speed divider. And I don't know, but the ratios are the same. So if we have a mechanical gain of 3, then we will have a speed reduction of 1/3. So they're inversely proportional to each other. So what he did when he was going through there, he gave you your mechanical advantage, which he was using torque out over torque in, or he was using and what he was saying is that you don't have to count teeth. You can use the diameter of the tube, or you could use the radius of the tube, or you could use the teeth. They would all come out to be exactly the same ratio. So which one you use, you'd come up to be the same ratio. So if this guy over here had 10 teeth, and then this guy over here had 5, then this is the driver, this is the driven. So our mechanical advantage would be 10 over 5, which would be advantage of 2. The speed we'd flip that around, because speed and torque are inversely proportional. So what that means is it would be the actual output gear would be running at 1/2 the speed of the input. That makes sense? So they're actually opposite of each other. So the formula he was talking about was mechanical advantage. How much torque do you multiply? And of course, all we'd have to do is just to find the speed is just do what? Flip the equation, because they're inversely proportional. So this is called a internal spur gear. And the big advantage of this, of course, is that the space that it occupies by the gear set. So I've seen these used a lot on shovels, big shovels, where the whole thing can move around. And you look under the side, you'll see a little ring under there. Then you'd see the internal spur gear would be on side that. So the biggest advantage of this, of course, is that the space that it takes. So what I would do, if I flip this around and I brought this gear out, the driver out, then it would be out here. And what that means is I would have this much space being occupied by my gear set. Well, what we do when we come up here and mount it and put it on the inside, then basically we eliminate the space for the driver, because it's inside, how much space it would occupy. That makes sense? Are we okay? This is kind of like a worm gear. This is what we use on our manufacturing line. We have the Festo line. The Amtro line uses one of these, and this is called a ball and screw. And what we do is we spin this guy right here. So this is what's spinning. And then what this does is it causes these balls to move, and they track. So if I'm spinning this direction, it would cause this guy right here to turn in this direction, which would cause the balls to go this way, which would cause whatever's attached to this carriage to go that way. And notice what they do is when they come off on this one side, this side picks them up, feeds them back around, drops them back in, no matter which directions it's going. So the balls inside this thing are constantly rotating. Converts rotary motion into linear motion with very little friction, able to transfer and withstand high torque loads. Minimum internal friction, high degree of friction. These guys, the only problem is they don't work real well like on vertical loads like this. They have a tendency to do what? back drive or move back. But horizontal works fine. This is actually the gear, the ball and screw. This is actually what's driving the carriage that takes it from the distribution over where the height sensor is, the ultrasonic sensor is. The Festo line doesn't use any of these. This is a planetary gear train. Can be used for high torque ratios in a small space. And what's really neat about this is we can actually use this as different gears. We can change between the drive and the driven. So I've seen them actually clamp this down, and then this guy right here spins, and this whole these planetary gears would spin inside here. And then if they clamp this one down, and then this is spinning, let me get that right. We can't clamp this one down right. So we can clamp this guy here down, and then this right here spins. That ain't gonna work. I gotta figure this out. There's the drive system. This was the original transmission that was used. Was like a planetary gear. I'll find that video and see if I can find it. Maybe can explain it a little better than I can. But there were several ways you could actually change speed or change torque with these gears right here. I'll see if I can find that. You see why it's called a planetary gear, though? Pretty, yes. Let's see, we don't need that. Gearboxes. So gearboxes, these are just basically boxes that contain multiple gears. So this is an example of a 5-speed transmission. And which one? Okay, so this is the input gear. And then basically what we do is when it shifts, it slides these gears in and out of the driver. So this is third gear. These two are third gear. These two are second gear. And these two are fifth gear. Oh, this is first gear. I went backwards. This is first gear, and this is fifth gear. They're not in the right order. So this is the driven. So you can see this is. So if we see big to little, what does that mean? Speed, yeah. If we see big to small, what does that mean? I'm sorry. If we see small to big, what does that mean? Torque, yeah. And this is the input gear. So I guess all these would be the driver, right? And these right here would be the driven. So this is first gear. I don't know if I said that right. So this is the driver, this is a driven, so this would be a torque multiplier. This is second gear, and you see this guy gets a little bigger, right? This guy is still bigger, so this is still a torque multiplier. Here's third gear. Here it looks like the driver is actually a little bigger than the driven. And then this is fifth gear. So here the driver is a lot bigger than the driven. So we start off and we automatically change the ratio. So this is what your transmission is doing. It's automatically changing the ratios as we move when it goes to the gears. Used to this was actually sensed by vacuum. So you had the vacuum being sucked in by the carburetor. When it sped up, the vacuum would actually change. And it would actually shift it. Now this is all done electronically. So your gears are shifted electronically. In fact, mine says it's got an infinite geared ratio. I don't know what that is. So what would be our ratio here? What would be the output? Is this going to be, Is this gearbox going to be a speed multiplier? Is it going to be, this is our motor right here. This is the motor shaft. And what they're doing is they're giving us the ratio. So this could be teeth, this could be diameter. It doesn't make any difference. It's inches. All you need to do is make sure everything's in the same unit. So let's say these are teeth. What would happen with this one? Would it be a speed multiplier or a torque multiplier? If it's a torque multiplier, what would it multiply the torque by, and what would it reduce the speed by, or vice versa? For that. So what we did was we figured out that if we have a gain that feeds a gain, then we multiply the gains together. And that's true whether you go down or you go up. So what we were saying, or what I was fixing to do, is I was fixing to come over here and take this prime mover and move it over here. I can get it and take it and move it over here. So here's my motor. Now we're going from what? We're going from big to small, right? So this right here would give us, what would be this guy right here? What'd you say? Everybody okay there? And then this one right here, because it's out over in, so here's our out, here's our in. So out would be 12, in would be 48. That makes sense? And that's what you're looking at. You're looking at out over in. So then we, right, that makes sense? 0.25, we okay now? Okay. Then over here, what would this be? Out, right? So here we're coming in here. So we're going 15 over 45. And what would that give me? So that means our mechanical advantage is going down, but our speed is going up, right? So what would be my mechanical advantage here? How'd you get that? That's exactly right. So it's what? Gains are multiplied together. And here we have a gain of less than 1. So what did we get? So here we said what? We said 0.25 times 0.33. And what did you say that gave us, Jeremy? I don't remember. I can't hear. 0.825. 0.825. But then when we take the reciprocal of that, so what's the reciprocal? The reciprocal, that's 1. Take the reciprocal of that, and that will give us our speed multiplier. 1 over 0.0825. So speed and torque are inversely proportional to each other. When you use this formula, what you're doing is you're calculating mechanical gain. You're calculating how much torque in, torque out is what you're calculating. It's still out over in. I mean, so it's out. So what we're doing is this is in, this is out. Over here, though, this is for this gear, this is in, and this is out. Okay. And gains, guys, are always out over in. Always out over in. Always out over in. So what we did over here is we came over here, Don, and we said, okay, out, 12, in, 48. And that came up and gave us 0.25. Then we came over to this set. This is out. This is where I'm going to. Whatever I'm running is connected right there. So this is going to be 15. Out is 15. In is 45. 15 divided by 45 is 0.33. And these are gains. And we call them gains even though they're attenuations. When you get less out than you put in, technically it's attenuation. But when we have gains, we multiply them together. That makes sense? And when you multiply fractions, you end up with less than you start off with, right? So it depends on where I put the prime mover at. It depends on this test right here, whether it's a speed multiplier and a torque reducer, or vice versa. We okay? Okay. I don't know how other we could come in and change the teeth. That's all we could do. Yeah, I understand that. So which side do we want to go from? Okay, so let's come over from this side and we'll change it. It's obvious that this guy here is going to be a torque multiplier. So let's say this has 54 teeth, and this right here has 283. Let's make them even. And there's a 284. And then this guy here has 38. And this guy right here has 68. So what would be my gain? Would it be speed or would it be torque? Yeah, we said we're right here. If we have a little feeding a big, it is a torque multiplier. If we have a big speeding a little, it's a speed multiplier. If we have a little gear feeding a big gear, it is a torque multiplier, a speed divider. If we have a big gear feeding a little gear, it is a speed multiplier and a torque reducer. But when we're doing our gains, we're calculating torque, because I don't know the speed. I do know the torque. I have no idea what speed this motor's running. This might be a variable speed motor, so I can't say it's got this. And all I know is whatever that torque puts out, then it's going to give me either more torque out or less torque out than I'm putting in. So what we're doing, so I'm looking at this one. So it's obvious this is in and this is out. But when I come over here and look at this one, we're looking at this set. This is in to this one, so this would be out for that set over there. You understand that? Okay. So over here to calculate this, out would be out 284 over 54. What? And this over here would be 68 divided by 38. So what ratio, what would we get out of this one? That's got 5.25. And these, by the way, these have no units. They're just gains. And over here, what would this give me? 1 point what? 78. So my total torque, so my torque out multiplier, this is not the actual torque. So I guess we'll say mechanical advantage would be equal to 5.25 times 1.78. What, Jeremy? Yeah, I heard that one. Now this is torque multiplier, and then my speed multiplier. My speed would be 1 over 9.35. So if I spell speed right. So this is a speed reducer torque multiplier. I keep hitting the thing right there. So first of all, you need to figure out what's in and what's out, right? And when you, anytime you deal with gains, outs and ins, it's always out over in. And this is mechanical. And this, you need that speed is opposite, right? We okay? So slip clutch, we have several of these on our manufacturing line over there. Engages and disengages the power transmission without stopping the prime mover. Can be used to control the amount of power transferred and the motion. Most of these are adjustable, so you can adjust this. And basically, what you're doing is tightening up these plates right here. So these plates are actually, it's called a slip clutch because the plates are actually slipping against each other. And of course, the tighter you make them, the less it's going to slip, right? That makes sense? So we have these. I think we got one on, I know we got one on the torque station, and I know we got one on the carriage, the one that moves. Bearings. What do you use bearings for? Normally it's when we transfer stuff from something that's rotating into something that's stationary. Huh? Yeah, but that's not a bearing. That's a clamp. What way though? Yeah, I know what you're talking about now. So what those things? So these things. So if you ever look, it's got this little groove right here. Yeah, I know what you're talking about now. And then on the side, they have these little balls. And then of course, when you release it, what it does is releases the spring on here and lets you snap them in there. Then it snaps closed. What a bearing does, it allows us to take something that, so I've got a motor. I've got a motor, and that motor has got to mount. And then I got a rotor in there spinning that I've got to be able to transfer that energy out here on the staff. So what we've got is something that's rotating, and we've got to transfer it through something that's stationary. So this would be where we would use a bearing. So you got your drive shaft you've got your rear axle out there, and you got to take it from your differential in the back, and you've got to run it through a tube out, and it's stationary, right? You understand? It's stationary, and then your rear wheels are spinning. So you're going from something that's spinning, and you're connecting it to something that's stationary, and this is where your bearings come into play. So your motor is stationary. But yet inside, everything is what? Spinning. And we've got to get all that stuff that's spinning inside the motor out to our drive shaft. Right? So you're going from something that's stationary, right? And you're connected to something that's rotating. So this is where the bearings come into play. So notice what we're doing here. This right here could be stationary. So it could be clamped down, not moving at all. And then what's happening, but this right here is what? This is spinning. So anything that goes from spinning to stationary, that's mounted on something that's stationary, you're going to have some type of bearing in there. And it's called a bearing because it's got to bear the weight. It's got to bear a lot of stuff, right? And we'll look at that, different types of bearings. A device that is used to enable rotational or linear movement while reducing mechanical friction and stress. Resembles the wheels. The main function of the bearing is to facilitate smoother rotation of the axis. So this, anytime we have friction in a system, what's going to happen? It's going to heat up, right? And friction causes heat. And what happens to metals when they heat up? Well, sooner or later. What happens to metals when we heat them up? If we heat metals up, they expand. If we cool metals down, they contract. What's that? No, retract. They get smaller. Okay, so if we heat metals up, they get bigger. If you cool them off, they get smaller. We call it the coefficient of expansion. So every metal's got a coefficient of expansion, which tells you how much it expands when you heat it up and how much it retracts or gets smaller when you cool it down. One of the physics classes I took in college was light, heat, and sound, and we had a steam chamber that we would put a metal rod in, and then we'd put a micrometer on the end, and we'd put steam in it. And we could literally see that metal do what? Get bigger. It'd expand. You couldn't see it, but you could see it with a micrometer, a dial indicator. And we did different metals like aluminum and steel and brass and different metals, and we figured out the actual coefficient of expansion. So different metals expand and contract at different rates. But I've got something out there, and and if I let these things get too hot and I don't compensate for it, then things are going to bind up, and we're going to have all types of problems. So the optimal goal of this bearing is to transfer that energy from a rotating device over to inside a stationary device with as little friction as possible. So the fidget spinners, that's what they call them. Those have bearings in them. And of course, you can't get her friction. If it had absolutely no friction, that means you could spin that thing and it'd spin for what? Forever. Yeah. So that's so fidget spinners, they were real big, and so I've got a few of them, and I've got one around here somewhere that I use for these examples. I might try to see if I can find it. Let's see if this video will play. And then after that, we'll. Live. Rotary motion, right? He called it static. From something static and something rotating, right? So, and like what we was talking about, like, you have bearings in your car, so every wheel out there has a bearing in it. You have a bearing in your steering wheel because the steering wheel is static, right? The post is static, yet you're able to spin your wheel around. And if you got a fidget spinner, you can definitely, most of the time you can see the bearing. You can see the bearing in there. Most motors have bearings in them. Well, in fact, all motors, all electrical motors have some type of bearing in them because we have to mount the motor. The motor itself is mounted stationary, and then it's got a shaft that comes on which we connect to. So these are the basic types here that he was talking about. And of course, he talked about radial loads and axial loads. You understand that? So radial loads would be something acting perpendicular to the bearing. So if you mount a bearing so if we mount a bearing like this, and then we bring a big old motor shaft in through it, and then that motor's got a big old rotor in here, then this is putting a lot of what? This is putting a lot of radial load on the bearing, right? And if something's out here pushing in on it, so think about your wheels, on your front wheels that you steer with. Well, there's bearings in there, right? You understand? And you come up here and you make a turn. Well, that turn is trying to push this wheel out, right, and push this wheel in. So when you make turns on your car, your front wheels have a lot of what we call axial loads, the axles. So axles pushing in toward the shaft. So we have to compensate for that kind of stuff. So the first bearing is probably the most simplest. These are just plain bearings. These are nothing but sleeves that would keep a lot of grease in. So the grease is basically the bearing itself, okay, between the rotating part and then the stationary part. This is the ball bearing. This is probably the most widely used out there. Reduces rotation friction, supports radial and axial loads. We call where these things spin at. So this has got a groove. This has got a groove right here inside of it. This has got a groove. Well, we refer to this as a race. So this would be what they call the inner race, and this would be the outer race. And so these are the parts. So you have the inner ring, or the the outer race. We have the cage. The cage is what's keeping the actual steel balls spread out, and so they don't move around and butts into each other. So it sets up the spacing. And then we have the steel balls, and then we have what we call the inner ring or the inner race. And you can see these are both grooved. And they do different things with these grooves to determine the loads, whether it's good for radial loads or it's good for axial loads. Are we okay? Okay. So this is a roller bearing. So a roller bearing, instead of using balls, steel balls, it uses rollers. And these can support, since we got more surface area. So on the ball bearings, all your weight is being supported right here. Right? You understand that? There's nothing going on there. But on the roller bearing, then you got all your weight spread across the roller. So roller bearings can support greater radial loads. Carries loads by placing the rolling element between the two races, able to carry heavier radial loads. Okay, we talked about the bearing parts. So basically, you still have the inner race, the outer race. But then on a roller bearing, you have a roller in there instead of a ball. Very simple, right? Everybody okay? James said, am I coming back to class? Oh, wait a minute. Probably not more efficient. In fact, they're probably a little less efficient just because of the slack of the chain. The chain can't be perfect. But the biggest problem we have with gears is if my driver is over here and my driven is over here, how would we get from point A to point B? Yeah, you'd have to have a lot of gears in between. You know, a few idler gears in between to get them between spots. So what's nice about change is the distance between your driver and your driven basically can be really, really long distances as long as you maintain your chain. You keep your chain aligned. Of course, the biggest problem we have on a motorcycle, so one of my motorcycles was a chain drive, one of the first ones I got, and keeping your back wheel perfectly aligned, because if it was off a hair, not only would it wear your back tire out faster, but it also wear the teeth out on your gear assemblies. Anybody who's ever had a bicycle, sometimes if they're not perfectly aligned, yeah, the teeth of the sprockets actually would actually wear down. And plus, you got to keep these things lubricated. That's the biggest problem with a lot of people in bicycles. They don't lubricate their chain. So one of the things that on a chain drive on a motorcycle, you usually had a lubricator back there. Basically, it was just a bottle that had oil in it, and it had a little whip on it that would ride on the chain and lubricate the chain. Anybody that's rode a bicycle and you put it up for a little while and you come back, chain's going to be rusted, right? And then you got to get it out of kink and work it out. Sometimes you have to replace the chain. So you have to keep these things lubricated, but in and out is exactly the same. So if this is my driven, this is my driver, and we don't call these gears, by the way, we call them sprockets. So we call them sprockets on chains. But the ratios are exactly the same. So if I was to measure this guy and measure this guy, well, if this is the driver and this is the driven, then this is going to be what we call a torque multiplier. And anybody that's driven a multiple speed bicycle understands that. So you start off with a little gear feeding a big gear, right? You understand? And then as you go through your gears, you change your ratio to get more speed because you don't use torque. But you'll see these people on the side of the road, their feet are going 90 miles an hour, and they're just barely going because they're in a real low gear because they're trying to climb. You see them climbing these hills, and their legs are going like this, but they're just barely going up the hill. So the ratios are exactly the same. What's critical though is the slack in the chain. We want very, very little slack in the chain. So a lot of your bikes will have another gear down here, and it'll literally have a spring on it that basically takes up the slack when you change the ratio between these gears. You don't want any slack in there. Of course, you got to keep them lubricated, and you got to keep your gears basically perfectly aligned. The sprockets perfectly aligned. If you don't, then over time the teeth is going to wear out on you. So, good video. We've already, they're expensive to maintain, lubrication, alignment, tension, and then drive components. So that's the biggest problem. The biggest advantage, of course, is the distance between your driven, and your driver and your driven. Basically, if you got a chain that can go long enough and you can keep it taut and you can line up everything, you could go a really, really long distance on these things. Belts. So what advantage does a belt have over a chain? Doesn't have to be lubricated. Good. It automatically has a little slack built into it. So if you start something up real fast, a chain might have problems and a chain might actually break, but the belt actually just give just a little bit. Belts, you can have a lot of slop. Belt, the alignments are not as critical between your driven and your and we don't call these, we call these pulleys. So we call them pulley wheels. Somebody saying something on virtual? Huh? Yeah, they're not near as expensive as chains. They're a lot more unforgiving than chains. So your car, just about anything that runs off your car that is not part of your engine runs through a belt, some type of belt. So you have a bunch of belts on the front of your car that runs your compressor, that runs your air conditioning compressor, it runs your power steering pump, and it might run even more. I've seen people with real high powered stereos that actually mount another alternator on their car just to run their stereo. So can y'all hear what he's saying? It's pointed against me. Okay.
I've seen that before, and they had to put a longer belt on it.
Yeah. So yeah, that's what I was saying. And so belts are a lot cheaper. They're easier to maintain. And they have different types of belts. So we have flat belts. We have synchronous belts. We have V belts, which is probably the most popular out there. These are usually the ones that's on your car, where they'll be real flat and they'll have teeth. The teeth works two functions, of course. They might go into a teeth on your pulley, but then also they actually cool the belt. They actually have a tendency to cool the belt down. Just the teeth themselves moving through the air have the ability to do that. So sometimes you'll see a V-belt that has teeth on them, and if you see those are in there just to to make the belt run cooler, it makes it more flexible. So this is a notched belt. So one of the advantages of these, of course, is they're more flexible, and then of course they run cooler. Multiple ply belts. By the way, these basically, how much you can actually pull depends on your width, right? And then how much is actually in contact with your pulley. So you'll see a lot of times where they use multiple V-belts, and they'll have multiple wheels, and then they'll run several V-belts coming through here. The problem with the advantage of this is that if one of your belt breaks, then odds are you'll probably be able to run a little while before you go out there and replace it. If you come over and have one of these and it breaks, then you're just out of trouble. You're in trouble, right? So these guys, if we use multiple V-belts, and we get the extra pulling torque by each one of them sharing the load. Conveyor belts. So let's quit right here. So what we're going to do is go ahead. We got very little left on this. So what we're going to do is go ahead. I'm going to go ahead and stop this.